Thanks for the invitation. Glad to be here.
Yeah, we love the background there. It's just a beautiful, one of the places you've been, right?
Yeah, that's Southwestern Africa, and it looks a lot better than my study.
Yeah, well, thank you very much. One of the key themes of the Long Now movement is to be able to consciously navigate between timeframes. Different processes operate in different timeframes, and our human perception is not particularly suited to seeing beyond the narrow frame of personal past, present, and future. But solving the problems we face today demands a multi-temporal, multi-scale approach, understanding different timescales and the interplay between them. This is something a geologist has to be able to do. The history of Earth begins with cosmology and planetary formation, then shifts to chemistry, the physicality of moving rocks, and finally biology, evolution, and human culture and industry, all operating on radically different time frames. This is Andy's recent book, published this year, A Brief History of Earth, 4 billion years in 8 chapters. This book takes you through the variety of timescales that are at work in our Earth, the history of its geology and the biology and where we are today. It's very well done. It's readable and comprehensible. And at least for me, it brought me up to date on discoveries that have been made in the last few decades, some of which have been quite surprising. Geology isn't necessarily something that is top of mind. It doesn't get a lot of media coverage, but there's a lot of very interesting work that's been going on, and Andy and many of his colleagues have been doing that work. And tonight we'd like to give a copy of Andy's book as a door prize to the first person who correctly answers the question we will pose. If you're in the room here and you think you know the answer, just raise your hand. And if you're in the Zoom room, type your answer in the chat. Jennifer's going to monitor the chat and see if anybody comes up with a likely response to this question. Now, if you've read Andy's book, you should know the answer already. So here's the question. What's the name for the fossilized microbial structures that date back 3.45 billion years, the earliest evidence of life on Earth? The fossilized microbial structures that date back 3.45 billion years, the earliest evidence of life on Earth. So anybody in the room willing to take a guess at this?
I know what it is, but I can't pull it.
You can't pull it out. You know, it's something, and you know what? Remember the landmass they've been looking at them in. They've been looking at them in Australia. Yeah. Yeah. Jennifer, we have anybody on chat willing to put this out? Okay, well, we got one response from the room that gets close. Anybody in the chat? I'll say the question one more time.
Oh, I did.
It's the name for the fossilized microbial structures that date back 3.45 billion years, the earliest evidence of life on Earth. All right, well,
It was Parsons.
all right, so Andy, do you want to give the answer?
It's something called stromatolites. I'll show a picture of one of these. They're the most abundant things in the geologic record for 3 billion years.
Yeah, it might take an expert to get the answer to that right off the bat, but and that answer actually surprised me when I read it. It's a reminder that life has been an active participant in the evolution of the Earth very early in its history, and it caused me to wonder, maybe life was going to happen. The conditions here right to have life happen. Maybe it's almost kind of an inevitable process if you get the chemistry right. So that links back to an issue we've dealt with before. If life is so likely to happen on Earth-like planets, and there are billions of Earth-like planets out there in the universe, how come we haven't met anybody else yet? And that's the Fermi paradox, and a question for another day. The other thing I'd like to bring to your attention is the photo image we're using for the event. Could you bring up the event photo for a moment here? It's a glorious photo, one of the NASA photos of the Earth. You see that photo. It's a little bit different than the one we usually see, because this is one looking down at the North Pole. And if you look sort of at the lower right section of that screen, you see a very, very big landmass. That is Siberia. And Andy will be talking about that landmass and a very important piece of geological and biological history that took place there some 250 years ago. So with that, I'll turn it over and let Andy tell his story. Andy, the floor is yours. Thank
Okay,
you.
well, let me just share my screen. Okay, can everyone see that? Thanks, George, for that introduction. Glad to meet with everyone this evening. I don't want to spend a lot of time lecturing, but George asked me to sort of introduce the subject for this evening, and so I'll show a number of slides. As George has already said, this discussion is predicated in a sense on a book that I published recently. And there were really two motivations for writing this book. I have to say that I've been continually surprised by how little people know about the planet we live on, that when we sort of look around and see the physical and biological features that surround us, how did those come to be? And I think even well-educated people tend to know very little about that. So in a sense, the book is an attempt to explain in accessible language essentially how the world came to be. And in doing that, hopefully it will induce some sense of the planetary legacy we've inherited, and that will motivate us to think hard about the future. And that introduces the second motivation, and that is to use the long history of the Earth, this immense time span that brought us to the present moment, as a framework for thinking about global change in the 21st century. And the punchline you probably already know, but I'll give it to you now, and that is, you live at a time which is unusual on the time scale of Earth history as a whole. This is not normal operation of the planet. And the reason it isn't normal is because of human activities. So that's the motivation. The second slide simply shows the major events that I discuss in the book and that provide the background for tonight's discussion. In the upper right is just a time scale. The Earth is a little more than 4.5 billion years old. And the first chapter, I discuss what I call chemical Earth. Basically, everything that is potentiated in terms of both the physical and biological structure of the Earth comes from Earth's accretion during the early solar system. And we know about that mostly from meteorites, which are bits of early solar system that either never accreted into planetary bodies or accreted into larger bodies and then were pulverized by later collisions. So they're tremendous sources of information. Then talk a little bit about the physical Earth. We're all familiar with the distribution of continents and ocean basins, of mountains, of plains, but how did all those come to be, and what dictates their formation and distribution? And as at least some of you will know, that has to do with the major operation of physical movement on the planet, something that geologists call plate tectonics, which is the movement of Earth's surface slabs as really driven by convection deep within the Earth. One of the questions is, when does plate tectonics begin? And there's a lot of discussion about that. Estimates vary over about 1 billion years, which probably has more to do with how you actually define plate tectonics rather than disagreement on the observations. And it really just shows us that rather than the formation of a physically modern Earth being essentially a doorway that we go through, it's really a corridor that takes place incrementally over a long interval of time. Then the next great event is the beginnings of a biological Earth. And that's just about as old. As George already talked about, we have evidence of life in the form in part of stromatolites, which are those laminated structures you see in the lower left. Those are found in some of the oldest, in fact, the oldest well-preserved sedimentary rocks on Earth. And we actually have a chemical record of biological activity that goes back a little further. So Earth has been a biological planet for most of its history. Moving upward, the next great event takes place beginning about 2.4 billion years ago, and that is the beginning of an oxygenated Earth. Had you been around 3 billion years ago, you would have asphyxiated in about 3 minutes. There was essentially no accumulation of oxygen gas in the atmosphere and oceans for the first 2 billion years of our planet's history. That changes beginning about 2.4 billion years ago. We get the permanent accumulation of oxygen in the atmosphere and surface ocean, not at modern levels, probably only 1% or 2% of today's levels, but it's absolutely transformational for biology. Then it takes a long time to get to the next major event, which is what I call animal Earth. And that really is the first time that we see large, complex, multicellular organisms on this planet. And in the middle panel in the lower center, you see some of the earliest animal fossils we have, and those are only 570 million years old. So that is to say that we don't have any evidence of complex multicellularity until the Earth is nearly 90% of the way through its history. Not long after that, as shown in this beautifully preserved, cellularly preserved early land plant in the right-hand bottom, about 475 million years ago, we see complex multicellular organisms moving on to land. Plants, soon thereafter, scorpions and the earliest insects. A little bit after that, the first vertebrate fossils and amphibians. So what you see is that the Earth becomes modern in both a physical and biological sense over immense timescales, almost incomprehensibly long timescales. And yet, many of the formational events are themselves much more rapid. So in a sense, there's almost this punctuated history where not much happens for long intervals of time. And then for reasons that generally have to do with the interactions between the physical and biological Earth, things change dramatically rather rapidly. And then if you look at the last 2 chapters, 7 and 8, we come to things where even in the geologic record, we have evidence of dramatic rapid events. Number 7 is called catastrophic Earth. And if you look above that number 7, you'll see there are 5 times in the last 500 million years when basically Earth's biological diversity collapsed and collapsed rapidly. Every one of those, as we'll see, corresponds with a time of rapid environmental change. And then finally, 8, way at the top of the diagram, is human Earth. The oldest humans that we know of, or oldest remains of humans that we know of, are only a little more than 300,000 years old, a mere blip in the long history of the planet. And really, it is within the past 2 centuries, in fact, mostly within the 20th century, when human activities, technological human activities, have resulted in a planet that is changing at rates that are generally not seen on million-year timescales. And so one of the questions that raises then is, are the changes that we are fomenting today leading us toward a sixth extinction? And that's really what I want to talk about. Some of you will have read Elizabeth Colbert's book, The Sixth Extinction. I really recommend it. And it again makes the case that we are living at a time of great biological vulnerability, and essentially the fate of Earth's biological diversity resides with us. So just a slide or two of history. It has not always been the case that people understood the fact of extinction. In fact, for early natural philosophers, as they were called in the 17th and 18th century, extinction would have been anathema, because if you admit there was extinction, that suggests that there was imperfection in the creation, and that was not something that people wanted to think about. That really changed because of the gentleman we see in this slide, Georges Cuvier, the great anatomist of his time who worked at the Museum of Natural History in Paris. And Cuvier studied fossil bones clearly related to elephants, things that we now would call mammoths and mastodons. But it was clear from looking at their skeletons that while these were related to elephants, they were not the same species as the modern elephants we see. And because elephants were so large, he felt that he could discount the possibility that somehow these were living in some remote corner of the earth and simply hadn't been discovered yet by explorers. And so he then essentially declared that they had gone extinct. And in the decades following that, geologists really came to understand that the geologic record is peppered with the remains of extinct species. Most species that have ever lived are extinct. And in fact, the pattern of those extinctions is really what underpins the geologic time scale, the Cambrian period, the Ordovician period, etc. Now, with Darwin, a mechanistic reason for extinction became apparent, and that is evolution. And thinking about the fossil record and extinction really was fairly static well into the modern. And I just show one slide here, a very important book published in 1944 by a man named George Gaylord Simpson, Tempo and Mode in Evolution. And Simpson was writing at a time that's sometimes called the neo-Darwinian synthesis. It's a time when genetics and population biology was merging with evolution and actually providing a mechanism for evolutionary change. And Simpson's book really is an argument that we can understand the fossil record in terms of these processes that population geneticists were starting to study. Now, what I find interesting about this book today is that in the entire book, I'd say there's about one paragraph on environmental change and essentially nothing about mass extinction. So we can say, well, what did Simpson actually miss? And what he missed is something that has become apparent through the tabulation of the fossil record, and that is that a lot of extinctions are actually clustered in time. And as we already mentioned, there are 5 times in the past 500 million years at the end of the Ordovician period, a prolonged interval in the so-called Devonian period, the end of the Permian period, the end of the Triassic period, and the end of the Cretaceous period, when, as you can see, this tabulation of taxonomic diversity just takes a nosedive, and more than half of the taxa that we know of don't survive the event. Now, there is no common causation for these, but all of them are associated with intervals of unusually rapid environmental change. So, for example, the extinction 66 million years ago at the end of the Cretaceous period, which we see here in this drawing, is associated with the impact of a large meteorite. And that was catastrophic and instantaneous. That's what really killed the dinosaurs and other less evocative creatures. But the extinction that I really want to draw your attention to is the one that happened 252 million years ago. It's the largest extinction we know of. It decimated an estimated 90% of all species living at the time. And this is, again, a rapid event. What you see in the picture on the right is actually a geologic record that preserves this extinction event. This is a place called Maishan in China. And if you sort of scramble up those cliffs in the lower part of the picture, those are late Permian limestones. They are full of the skeletons of animals, algae, and protozoans. And when you get to the top of that cliff, at a point where you can put a knife blade, they all disappear. And as you go up above that and continue to climb the cliff, you find only a very low diversity of animal life in the oceans, and that will slowly rediversify over millions of years. So this is a rapid event, and we now know what caused it. This is what George was talking about in terms of Siberia. There's a group of rocks called the Siberian Traps. And these traps are volcanic rocks that document volcanism on a scale 1,000,000 times greater than anything ever witnessed by humans or our immediate ancestors. This was lavas that were up to 2 kilometers thick, dispersed over an area the size of Australia. So it was really serious stuff. Well, how does that actually relate to extinctions? Well, there are consequences of that rapid volcanism. One was that there was a rapid increase in carbon dioxide, causing global warming. Second, because of that increase in carbon dioxide, some of the carbon dioxide goes into the ocean. It lowers its pH, something that's called ocean acidification. Actually, very much complicates the mechanism of making a skeleton in marine animals. And third, because the oceans are getting warmer and they can't actually carry as much oxygen as colder water, we get oxygen-free water masses, anoxic water masses in the subsurface of the oceans. Now, if you've been reading the newspaper, those should be familiar things. They're exactly what's happening today. And one can ask, how does that physical change precipitated by rapid increase in CO2 affect organisms? Well, back when I first got interested in this, there wasn't any literature on it. And so having thought that, well, maybe CO2 is a killer here, I actually went with my friend Dick Baumbach, and we literally spent a couple months in the library looking at decades worth of physiological experiments that were done to look at the essentially consequences of imposed high CO2 on the function of different organisms. And that allowed us to essentially make predictions about the vulnerability of different late Permian species based on features of their biology that we could infer with confidence from the geologic record. And what you see here is just 2 diagrams, both going through the interval that includes the extinction and showing diversity through time. The upper one is those taxa that the experiments that we were able to dig up suggested should be vulnerable to increased CO2 based on their skeletal biology, their metabolism, their anatomy, things like this. And you can see that they just get punished. Most of them disappear. Whereas those taxa that we would predict to be relatively tolerant, while there's some loss in diversity, they really don't notice a mass extinction. So the first conclusion then is that what we learn about the biology of living organisms allows us to relate the environmental change of rapid CO2 increase at the end of the Permian period with the major extinction. And since that time, there's been a huge amount of experimentation, really not to explain the end of the Permian, but to help us understand the 21st century. And they have shown that there really is a resonance between what happened in the past and what is being set up for the future. So coming toward the end, then, that introduces this whole idea of the Anthropocene epoch. There's actually a movement to create a separate geologic time interval for the last maybe 200 years of history, because this is an interval in which the activities of humans have really come to dominate the planet in an unprecedented way. And they're leading, as we'll see, to changes in the planet that are much more rapid than what we have seen really on a time scale of millions of years. And as we'll see, that there's no question that that rapid environmental change is related to human activities. And so the question then is, are we seeing a repeat of things that have happened in the past with rather untoward biological consequences? And just a word about, in some ways, the obvious. In many ways, we live in the golden age of humanity. I think none of us think it's unusual to get on an airplane in Boston and get off in London 6 hours later, but your great-great-grandparents would have been astonished at that. We have eradicated smallpox, long one of the major scourges of the population, and polio may go the same way. We have had remarkable increases in crop productivity. And one of the consequences of that is that the human population has mushroomed. The human population wasn't that different in the time, the population size wasn't that different between the time of Caesar Augustus and the time of Elizabeth I. And the people didn't live all that much differently either. But particularly beginning with the industrial age, things have changed. And you can see on the left how population has grown. We are about to cross 8 billion people. And that, of course, puts strain on all sorts of resources. On the right is a related image, which simply shows the relationship between what's called the Human Developmental Index, that is basically standard of living, which goes from low on the left on the x-axis to high on the right, and essentially the biological footprint of individuals expressed as a function of how much land it takes to support a single person. And what you can see is something that, again, makes intuitive sense. That is that for those people at the lower end of the Human Development Index make rather minor use of Earth's resources, but as standard of living goes up, so does the human footprint on the environment. You can see the U.S. is well over on the upper right-hand side. It becomes even more something to think about, in that I think everyone who lives in any of the countries that are on the low end of the Human Development Index quite reasonably would like to increase their standard of living. And one of the correlates of that is that means that as we help those who are less fortunate than we are, their footprint increases as well. And so in combination, those two graphs really help to explain how we got to where we are today. Now, many of you have read in just the newspapers and magazines that there have been a lot of sobering reports on the biota in recent years. As it says here, in North America, bird populations have declined by about 30% in the last 50 years. There have been studies in Europe showing that insects whether you measure it by biomass abundance or number of species, have declined precipitately just in the last 15 years or so. On the Great Barrier Reef in Australia, there was a 50% decline in coral reef coverage between 1985 and 2010. And an important thing to note here is that the major drivers of those changes have been land use change, pollution, overexploitation, and invasive species. That is to say, most of what has happened over the last century is not principally attributable to global climate change. And that brings me then to the almost the penultimate slide, and that is that now what is going to be the major influence on our planet in the future is just revving up, and that is global climate change. We know why that's happening. It's happening because the amount of CO2, a potent greenhouse, is increasing in the atmosphere, as is methane, an even more potent greenhouse. This famous Keeling curve on the lower part simply shows measurements of CO2 through time. And in my lifetime, the amount of CO2 in the atmosphere has increased by about a third, and it shows no signs of slowing down. We know from the isotopic chemistry of that CO2 what the source is, and the source is principally the burning of fossil fuels. As you see on the upper right, there is some contribution from the burning of biomass, both in the tropics and in the temperate zone, but largely it's fossil fuels. And it's interesting that only about half of that CO2 production ends up in the atmosphere. Some of it goes into the biota, and about a quarter of it goes into the oceans. And that's what drives the change in the pH of the oceans, which makes it harder and harder for many organisms to make particularly calcium carbonate skeletons. Now, just indicate that by one more slide from the Great Barrier Reef. Not only is the world getting warmer, but in association with that, we're getting more and more extreme weather. And that may be more damaging than the slow increase of mean average temperature. In the Great Barrier Reef, there's something called bleaching of corals. That is, when the temperature goes above a certain degree, the algae that live within the tissues of the corals and actually supply them with food are basically ejected. And it's called bleaching because the coral turns white and will usually die. There was extreme weather, warm weather in the northern Great Barrier Reef in 2016, and that killed about half of the corals in the northern part of the reef. In 2017, it whacked the central part of the reef. And in 2020, it was pretty much universal in its destruction. This is the kind of thing that might have happened once in a decade or two, a century ago, but now it's becoming common and repeated and calls into question the ability of the reef to actually be sustained over the time scale of this century. And as I point out in the lower right, that this is happening as pollution, overfishing, ocean acidification, all of these things are happening and actually accelerating. So it's, I think, a very real question, as we see in this next slide, as to whether your grandchildren will actually be able to see a Great Barrier Reef. This is just a picture from a research reef tract, and all of the white corals have suffered bleaching. Final slide then, and then we can hopefully get into discussion, is to ask what's going to happen in the future. And I like to think of this as sort of, if you've read A Christmas Carol, like Charles Dickens, he talks about the ghost of Christmas yet to come. And the ghost of Christmas yet to come isn't telling Scrooge what definitely will happen, but rather what will happen if Scrooge doesn't change his ways. And in a sense, I think that's the way to think about the rest of this century. We have the ability, if we have the will, I think, to mitigate the worst of this change. I mean, in some ways, the rabbit is out of the box, but we can, I think, minimize the damage through personal choices. You can make choices about the food you eat, whether it's local or is trucked in or flown in. As many of you know, different sources of protein make very different demands on CO2 release. Various options for heating and cooling our buildings, for driving, for flying, can all contribute to essentially slowing or minimizing rises of CO2. And importantly, the way we vote makes a great difference, because governments, some of you may disagree with me, but my pessimistic sense is that governments are unlikely to do very much unless they're actually pushed by the population. There are also things that have to be done on a societal scale. Clearly, the movement toward renewable energy sources, which is, I think, accelerating, fortunately, and which really has to happen. You know, we couldn't have another 200 years of reliance on petroleum, natural gas if we wanted to, because there isn't enough there to sustain it. We have large supplies of coal, which is, of course, the probably the dirtiest or most damaging of all the fossil fuels. We now have operating plants, at least at the the project status, removing CO2 from the environment. At this point, it's done on a small scale and it's expensive, but it is a technology for the future. In terms of conserving the biota, yes, we need to invest in parks and refuges, but because the climate is changing in every one of those parks, and a park that acts as a good refuge for a species in 2020 may not do so in 2100, we need to create corridors so that there can be movement from one of these areas to another. So that's really all I wanted to say by way of introduction, and move on to discussion. So have at it.
Andy, thank you. That was very, very insightful and also very moving. And I think I like and appreciate your, your nuanced positivity about the future. And I think that's, that's good. So thank you very much for that. I wanted to start off with a couple of questions, and then we'll open it up here. And also people could put their question in the chat. I just wanted to go back a bit to the issue of various timescales, and the slide you had where you talked about going to China, Meishan, China, and looking at that, that rock wall or the cliff, and and climbing up this massive, structure with all the layers of sediment. And what did you say the Permian boundary layer was? How big was that?
Well, the boundary layer is a surface. There's, below that surface, there is diverse life. Above that surface, it's all gone. So it's something that must have happened on a time scale, possibly decades, centuries, maybe 1,000 years, but no more than that.
Okay, so it was in the context of the geology, which is measured in millions of years. This was an event that was a flash for geology, but a monumental shifting for the biological world at that point, right?
Yeah.
Yeah. And that it sounds like the driver of the Siberian Traps event, that Permian extinction, was the CO2 that was released by the volcano. It wasn't, it wasn't sort of the ash that got thrown up like we think of, recent volcanoes. It was really the cumulative buildup of the CO2 that just washed over the earth and changed the chemistry and the meteorology, and that eliminated those vulnerable species. Is that?
Yeah, that's pretty much what the record tells us. You need some way to make that regional event global. The only way really to do that is to put a lot of gases into the atmosphere, and the selectivity of the extinction, I think, is actually the biological testament to that happening.
Yeah, and you also talked about the fact that that event essentially hit hardest the species that were dependent on skeletal formations. Is that kind of the...
Well, it's a little more nuanced than that. I didn't go into it, but I often, when I talk to my students, I divide the marine biota into what I call couch potatoes and other more active things. So there are some species like corals, which have a major dependence on massive carbonate skeletons, but their biology gives them very few options for actually modulating the fluids from which they make those skeletons. So corals are really vulnerable, and basically literally all Paleozoic corals disappeared at that boundary. The corals we see today are descended from sea anemones that survived the boundary and then later evolved skeletons. And you can contrast that to clams, which obviously make a skeleton of the clamshell of calcium carbonate, but clams have a much greater physiological ability to actually modulate the fluids from which they make their skeletons. So we would predict that clams would be able to tolerate environmental change better than corals. And A, that's what the geologic record tells us. And B, that's what 21st century physiological experiments tell us as well.
Okay, so if we're looking ahead, then we'll lose the corals, but we maybe still have some clams around. Is that?
Well, it's interesting. You know, there are people who whose lives depend on clams. So you have people in southeastern Australia who are very interested in what happens to oysters. There are people in Washington State the same way. And the interesting thing, and this is both disturbing and maybe helpful or hopeful, is that there's population variation. So it may be that if you have 1 million oysters, 950,000 of them will essentially die because their life cycle is disrupted by this global change, but some of them will do okay. And so one possibility is that we will be able to maintain both ecosystems and some of the services they provide by actually selecting and propagating those species that are, or those real populations or individuals that are better able to tolerate these. There's a guy named Steve Palumbi at Stanford who's been looking at coral species around the world. And, most coral species, I think, are in very, very grave danger. But there are some isolated populations that Steve has found in Tahiti that seem to be able to tolerate this change much better than others. And, one possibility is that we will be able to maintain things like reefs by transplanting more tolerant populations. Now, that's a hugely expensive proposition, but it may be one way that we can actually, our grandchildren may actually see reefs.
One more question along this line, and then we'll turn it over, and that is sort of the rapidity of the CO2 buildup from the Permian transition and the volume of it. Can you give us a sense of, was it more CO2 than we're seeing released now with the combustion of fossil fuels, or less? And was it slower or more rapid than?
Yeah, well, within the ability of within our ability to actually say that, because there are limits to time resolution in the past, it has been argued that the rate of CO2 increase is actually higher today than it was in the Permian. But either the good or bad news is that the time period over which that CO2 increases today cannot possibly go as long as it did in the Permian, because we simply don't have enough fossil fuels, even if we wanted to burn them. So in a sense, we think that at the end of the Permian, CO2 may have increased by as much as an order of magnitude. And we're thinking about doubling of CO2 today. So at the end of the day, it was worse at the end of the Permian, but that's a question. It's a question of degree rather than fundamentally what's happening. And B, there are three ways that a population can actually adjust to environmental change or react to environmental change. One is it can actually adapt. So on some timescales, evolution can produce tolerant populations, but when the change is as rapid as it is today, the percentage of species that can do that declines rapidly. Second, species can migrate, but in the modern world, where a species that's in Louisiana today may not be able to migrate to Illinois because it has to pass through urban areas, it has to pass through croplands, across superhighways. So just the physical structure of modern landscapes is such that it makes migration more difficult. And the third option is simply to go extinct. And that is, at least at times in the past of rapid change, the dominant consequence.
And the one other thing that exists today that didn't exist in the Permian is a dominant species that has the ability to change what it's doing going forward.
Exactly. Yeah, that's the key point to underline. If we want to do something, we can.
Yeah. All right, I want to open it up a little bit. Yes. And I think that speak towards that. I think that will pick you up.
My question is, towards the end of the Cretaceous period, there was also a similar volcanic event, the Deccan Traps in India. Did that have a similar effect on the atmospheric composition of the CO2 percentages and then on the biota as well?
Or can you repeat the question for the Zoom?
There was another
Near the
volcanic
end of the
event at the end of the Cretaceous.
Called the Deccan Traps in India.
Deccan Traps in India. You cover that. And the question was how.
About this.
Oh, thank you.
Near the end of the Cretaceous, there was another large-scale volcanic event called the Deccan Traps. And was that something that also had a similar effect on the atmosphere, the CO2 composition and its effect on the
Yeah, that's actually a really good question. It turns out that every now and again, and fortunately now and again is, maybe every 20 million years or so, the Earth lets go with very large volcanoes. One of those happened at the end of the Triassic period, and that seems to have caused another mass extinction. There's also large-scale volcanism right about the time of the Cretaceous mass extinction. Now, it turns out that we can actually discriminate time well enough to know that what seems to correlate with that volcanism is actually a somewhat warming of the world, but nothing too dramatic. And that what really correlates in time with the extinctions is actually the impact. Also, it's interesting that if you look at the selectivity or lack thereof of end Cretaceous extinction in the marine realm, it's very different from the end of the Permian. And so, you're right. There are other times of transient environmental change associated with massive volcanism. And for reasons that I don't think we understand entirely, some of those resulted in biological catastrophe and some of them didn't. Hope not. I'll have nothing to do if it is.
The commissioner for the city of Somerville's Energy Use and Climate Change Commission, is that right?
Yeah, that's right, yes, although, I'm so confident about COP26 that my question is actually is not about human-induced climate change. I'm actually curious, after the other 5 mass extinctions, there's a pretty rapid re-diversification or repopulation. And I'm sort of curious if there are conditions we can put in place to ensure the most rapid re-diversification as possible. What's in that time capsule that we should leave?
Yeah, that's a good question. And sometimes you will read people who say, well, we shouldn't worry too much about mass extinction because in the aftermath of mass extinction, the biota has always re-diversified. In a way, that's the good news. The bad news is that the time scale for that is millions of years. So in terms of any world that you or your grandchildren or their grandchildren might experience, extinction is permanent. Now, there may be ways of accelerating rebound. I think we can probably, we know some of the processes that cause speciation. On the other hand, I think there's still a lot of uncertainties about how ecology reconstructs itself. And I think in the absence of that knowledge, it is difficult to know, even if we can somehow technologically reconstruct, some aspects of, let's say, clam diversity or deer mouse diversity, how that will react in an altered landscape. This has to do, everyone here knows that there are some interesting ideas about sort of, in a sense, reconstituting mammoths, essentially making elephants that have some mammoth genes in them that would be at least somewhat more like mammoths. And one of the issues there, there's lots of issues which probably go beyond tonight's discussion, but even if you could reconstruct or reconstitute a mammoth, not clear that the world the mammoths lived in exists anymore. So you ask a really good question, and I'm sure there are people who are thinking about how we might assist the reconstitution of diversity, but A, that's extraordinarily difficult, and B, at best, the timescales will be centuries. So we're better off trying to limit diversity loss in the first place.
Yeah, thanks. There's a John, and then we have some chat questions. So
Go ahead with the.
Okay, well, let me try one of these, see if I get it. And you talked about points of vulnerability and what's things. One of the things that will affect certain populations and species is sea level rise. If we lose ice sheets and sea level rises, 10 meters or I think what was the reference here was to, 10 meters. There's a lot of the coastline that will be affected significantly. And we can certainly think of one species that will be doing a lot of migration to try to avoid that. But just from a geological perspective, is sea level rise kind of a significant factor, or how does that compare to the CO2 levels and the global warming impacts?
Yeah, that's a good question. And there's a lot of things that affect sea level. So if you look at the geologic record, one of my professors in graduate school characterized Earth history as the seas go in, the seas go out. So there's almost continual sea level change. In general, rising sea level gives shallow marine populations expanded opportunities for living and diversifying. So those species you'd expect to do well. One group of species that would be vulnerable, and it's a very important group in terms of marine ecosystems, is mangroves. And I think seagrass communities in the temperate zone as well, or salt marshes. So quite a few marine animals actually spawn in mangroves in subtropical and tropical environments because they're tremendously rich in resources. And I think mangroves would be somewhat vulnerable. I do think salt marshes will be vulnerable, but as George alluded to, I think the species that I can think of that is just about as vulnerable as anyone is the Floridians. If you live in Florida, you may want to consider selling your property before the end of the century.
Yeah, I think that raises the question of those vulnerable populations like salt marshes and mangrove swamps. Now, those are, you could say those are sophisticated ecologies that are going to be at risk. And I'm just wondering if in the Permian extinction, if you had similar sophisticated ecologies, or was the kind of the networking of species and food chains, the same level of complexity, or was it a simpler world back then?
I think in general it was broadly similar. Most the mangroves that we have today are flowering plants, which didn't exist 250 million years ago, but it's clear that there were mangrove-like species at the time. Grasses didn't exist then, but it's clear that there were salt-tolerant ferns and things like that. So I don't know that the ecosystems that we have today are markedly more complex than the ones we had then. And so I don't know that either makes them modern species more vulnerable or provides some resilience against change. I think we just can't answer that.
Okay. John Kafarski?
So this is a question that involves probably a great deal of speculation on your part. So I apologize for maybe taking out of your area of discussion, but you've raised an interesting distinction between the CO2 and the warming. And one of the things that has been proposed is, as they call it, solar geo, the idea that let's imagine the magic sunshade, that we're able to shade the solar radiation hitting the Earth to the point where we not only stop the warming, but actually, somehow we managed to get us down to the pre-industrial global temperatures, and we've whipped the temperature up, but we've still got the CO2. I'm curious to know how you would imagine the effects of that on extinctions and species, et cetera.
Yeah, no, that again, this is something that's been debated a lot. The idea is that so-called geoengineering, one could put sort of sulfur aerosols in the upper atmosphere and they would reflect sunlight, which would have the effect of cooling the Earth. But as you already mentioned, it would do zero to the amount of CO2 in the atmosphere. And so that would, as long as we're burning fossil fuels, that's going to keep going up. And it turns out that the length scale on which those aerosols remain in the upper atmosphere is maybe a year or two. So the problem with geoengineering, or a problem with it, is that once you start it, you can't stop it, because the 2 years after you stop it, it's like you never started it in the first place. So while there are thoughtful people, including some in the Boston area, who are trying to understand that and see how it would work, it's a massive undertaking. You would need a very large fleet of 747s on a daily basis to keep those aerosols in the upper atmosphere. And at the end of the day, it might buy you time, but it doesn't stop the problem.
And what does stop the problem?
I think that there are two things. One is we can at least slow down the rate at which CO2 is increasing and maybe start to bring it down by largely, I think, by moving to different types of energy. We all know about renewables, wind energy, tidal energy. I've been reading a lot more about a hydrogen economy. Fusion has actually come back onto the table again. All of those things will keep CO2 from going up at the rate it has been. They don't bring CO2 down, but as I alluded to, there are pilot plants that really literally scrub CO2 from the atmosphere. And as I said, the cost of removing a ton of CO2 from the atmosphere at the moment is pretty high. And the amount of CO2 you can actually remove with these pilot plants is pretty low. But that shows us that there is a technology that if developed on a larger scale, could actually remove CO2 from the atmosphere and help move us back to where we were, say, in 1960.
Yeah. We have another question from the chat. It's on a different tack, I think, and it's asking if there are useful things we can learn from a better understanding of indigenous cultures and their cultural attitudes towards the natural world.
Yeah, that's a great question. And I am not an expert on this, but I've always been impressed by the intimate knowledge of the natural world that people in indigenous cultures display. I remember talking to an old friend of mine, a guy named Jared Diamond, who best known probably to you for writing books like Guns, Germs, and Steel, but Jared spent a lot of his life being an ornithologist in New Guinea. And he said he just couldn't get to step one in that work until he learned to look at the landscape like his guides did. And those people knew the world very, very well. I think in some ways, the predicament that we've gotten ourselves into is not independent of the reality that modern Western humans are in some ways cosseted from the environment. We don't know much about it. We don't think about it. Whereas for many cultures in the past, in many different parts of the world, you couldn't survive without an intimate knowledge of the environment. So yes, I'm sure there are many, many things we can learn. It is interesting that there's been a lot of sort of archaeological work in the Amazon over the past decade or two. And, we like to think of maybe the Amazon as being this pristine area, basically stewarded beautifully by indigenous cultures. But in fact, before Europeans came to the New World, much of the Amazon had actually been cut down and was used for crops. So, there are things we can learn, but there are things where indigenous cultures have made their own impacts on the environment, and we might learn from those as well.
Yeah. That reminds me, as just a reminder of our December talk, is an architect, Cristina Alonso Pereño, and one of her focus points of her talk is going to be on the fact that architecture, at least in the modern Western world, has tended to separate us from nature and added to that, kind of that archetypal notion of nature is to be excluded, it's evil, and part of her work is to try and embrace nature and bring that back into the architectural concept and attitude. So I think that's an interesting lesson that perhaps hearing about December. Any other questions from the audience? I have a closing question for you, Andy. Before we kind of break the formal session, we have an opportunity for informal conversation for a period of time afterwards. And as we used to do when we were always, kind of in person, we'd call it, we'd convene at the bar, go down solve the problems that have been raised, after the formal conversation. So we'll do a little informal chit chat after we formally close. But so here's my question, Andy, and that is, back to the issue of time shifting and the different time scales, let's go out into the future. I don't know, a couple 100 million years, a nice geologist time chunk. And let's make the assumption that fossil fuel combustion and other pollution stops in the next century or so, optimistically through reforming anthropogenic practices and not from the extinction of the human race. So take us to a geological site with layers from the late Cenozoic and whatever follows. What would you look for, and what do you think we might find?
Yeah, this is a question that people have actually thought about, in part the people who would like to define this Anthropocene epoch in a formal geological way. And the first thing to say is that on the time scale of hundreds of years, not millions of years, we won't be burning fossil fuels for the simple reason that, by the end of this century, I think we will have burned all the natural gas and petroleum that's available to us or close to it. And on a scale of, even if we continue to burn coal, we're talking about hundreds of years at most. So there's lots of reasons to move to different kinds of, economic reasons to move to different kinds of power and energy. But I think one of the things that you'll find, as geologists, in my world, history is recorded by sedimentary rocks. That is just sands or limestones or muds that accumulate through time, and those give you a time series. One of the things that we find is that the amount of toxic metals, the amount of plastics, the amount of there's even people who've done beer can stratigraphy in the Gulf of California. Just the things that are being deposited in sediments that are a result of human technological activity. I mean, one of my, I hesitate to say favorite because I think it's a terrible thing, but it's been estimated that humans dump a garbage truck full of pollutants into the oceans every hour. And so there will be a discrete record resolvable by geological techniques of basically the rise of 20th century technology. And there will be, again, it's yet to see the magnitude of extinctions. Some extinctions have already happened. 10% of indigenous Australian mammals went extinct since Europeans came to the continent. So there will be some extinction that will leave a geologic record, and we've yet to see how deep those cuts will be.
I also recall reading about the arguments about defining the start of the Anthropocene epoch. And I think there's a term called the golden spike, which is the particular item that is used to define the start of the new epoch. And do you have any thoughts on what the golden spike for the Anthropocene might be?
Yeah, it's a good question. And actually, I'm in a interestingly privileged position here that I am the only person to lead the definition of a new geologic period since the 19th century. There's something called the Ediacaran period, which moves the record back in time. And the golden spike just has to do with the definition, because the definition of the start of a period or an interval of time is a point in the rock record, and everything above that point belongs to period B, and everything below it still belongs to period A. So you really want to find a point in the rock record where something really interesting happens. At the end of the Permian, you have this huge event. The Ocran period that I defined was the end of a global glaciation. And so the question really is, what can we actually see in the geologic record that shows the mounting influence of humans? And there are people who would say, well, you can go back to 10,000 years ago and you see the effects of humans burning forests in various parts of the world. And that's true, but it's hard to see how those form a timeline. On the other hand, when you start to have the Industrial Revolution, you start to see things all over the world that really mark the beginning of a qualitatively different influence of humans. So I think it is likely that the golden spike is going to be chosen at some point in the actual geologic record that corresponds to the Industrial Revolution.
All right, thank you. Andy, it was wonderful. Great to have you. It was a lot of fun. It's a great talk. So we'll do a virtual. Over to Jennifer for the formal closing, and then we'll get back to informal.
George, and thank you very much, Andy. That was fascinating. I really enjoyed that. Thank you all, too, for joining us this evening, both here at CIC and those of you at home on Zoom. I hope you also found this conversation rewarding. I would like to thank our production team, Mary and Anurag and Gary. Thanks so much for supporting this. Do a great job. We will have an informal conversation, as George mentioned. But first, I'd like to encourage you to please visit our website, longnowboston.org. Follow us on social media. Please consider joining as a member and volunteering with us. I guarantee you'll really enjoy that. Please sign up for our event in December with Christina. And I think if that's it, thank you, George, for hosting. And we will move into an informal conversation now for those of you at home who will be leaving us. So please feel free to stay on the Zoom. We'll open it up for everybody in the Zoom room. But if you are leaving us this evening, thank you so much for attending and stay well. Good night.